Swayam Prabha. Digital India. Educated India.
Good morning, everyone. It is a pleasure to welcome today's speaker, Professor Ramprasad Saptharishi. Professor Saptharishi is a faculty member at the School of Technology and Computer Science at the Tata Institute of Fundamental Research. He completed his PhD at the Chennai Mathematical Institute under the guidance of Professor Manindra Agarwal. Following his doctoral studies, he worked at Microsoft Research India and later at Tel Aviv University before joining TIFR. His research lies in the field of theoretical computer science with interests including pseudo-randomness, de-randomization, and algebraic circuit complexity. He is widely appreciated for his contributions to algebraic computation and for making complex mathematical ideas accessible through his lectures and expositions. We are truly honored to have him with us today as he is a proud alumnus of PSBB. I'm sure this lecture will be both insightful and inspiring. Please join me in warmly welcoming Professor Ramprasad Saptharishi.
Thank you very much for this kind introduction. It was very nostalgic coming back to IIT after a long time. And then I entered this room and then I saw the uniforms. Then it took me further back. Okay, so this talk is going to be a very weird talk. Okay, I'll tell you right at the outset. People would have told you not to play with cards and whatnot. I'm going to show you card tricks throughout. Okay, but since I have to pretend as if this is a research-oriented talk and there is some research component to it or something, I will tell you there is something called a Mandelbot Set and we will try to find connections to it. But I'll be honest with you, I don't care about the Mandelbot Set. I mean, we are going to care more about the card tricks. Okay, so let's start. So nowadays, for instance, you can't start anything without disabling ad block. So let me show you an ad. So this is Tata Institute of Fundamental Research in Bombay. It's a beautiful campus. When we are not working, we are mostly playing board games, we are doing card tricks, we are going on hikes, etc. It's a really nice campus. If you ever get a chance to visit, please do visit. And I'm sure some of you would want to take up research at some point. So the School of Technology and Computer Science at TIFR is one such place. We have a computer science and LITS program, yada, yada, yada. Okay, advertisement over. Okay. Okay, so before I start, I want to just do a brief survey. So if you have a smartphone, just scan this link, or if you want, you can just go to menti.com and enter this. Okay, it should take you to like a questionnaire sort of a thing about hobbies. Actually, I don't remember what the first question is. Like, what is a serious hobby that you have? And I have put serious in quotes because I'm not going to define it. The whole point of it is for you to figure out what that means. Okay, I let people look at it because the only way I can look at responses is by going to that slide and then everyone gets to see. Okay, maybe now it's safe to. What happened to that thing? Okay. So music, crochet, quizzing, coding and cycling, playing guitar, watching football, coding. Okay. Okay, video games, poker, great, art. Yeah, there's one more right after this, which I think we'll get to shortly. Okay, good. Okay, now here is a second question. So here is a second question, which is, what would you say are some characteristics of whatever you will call a serious hobby? Okay, this is amazing. So, okay, anyway, so let's just, oh, it works now? Okay, it doesn't matter. I mean, like, this is just supposed to. Okay, or we can just ask, what are some things that you will sort of say is that, oh, when does something constitute a serious hobby? Like, in my opinion, if you say, I like watching movies, that's not a serious hobby. I mean, there needs to be more stakes. Huh? Huh? Okay, anyway, you can answer these. You can think about it more, if you ever have a different thought, you can sort of add the thing. Okay, so these are the only 2 questions. I just want you, this is more to prime you towards what is going to happen in the talk. So let me start by telling you what a Mandelbrot set is, and I promise to you that I will only spend 2 more minutes on it, and then we will go into card tricks. Okay, so a Mandelbrot set is it often shows up when you're trying to understand something called an iterative process. So there's something called complex numbers. Some of you may have seen this in school. It's not very important, but think of just a function where you feed it a complex number, it spits out a complex number. That's all this function does. So what we are going to do is we are going to start off with the function being 0, with the value being 0, and we'll imagine hitting this function again and again and again. Think of a button that says, okay, I now want to apply f. You apply it again and again and again. This complex number will keep evolving. And sometimes you might want to understand what happens if I just keep doing this again and again. A few things could happen. Either this number becomes so large that it becomes something like infinity. Maybe that happens. Or even after pressing multiple times, it sort of stays bounded, like within some, whatever that thing is. And even within bounded, there could be interesting things that happen. Either it is the case that it converges to a single point, or maybe it keeps oscillating between 2 points or 3 points or something. Or maybe it stays bounded, but there is no predictable pattern in what is happening. There's no like small period or anything of that sort. Any of this could happen. So I'm going to give you a bunch of examples, and each of this is going to have a specific complex number c, and we're going to try and understand for what sort of values will this stay bounded, when will it explode, when will it converge, etc. So let's look at the first example. Suppose the function is you are going to add the complex number c to whatever you started off with.
Have you guys seen complex numbers?
Okay, if you want, think of this as just a rational number, real number, your favorite number. So suppose it's 42. My favorite number is 42. No matter what number you give me, I'm going to keep adding 42 to it. What will happen to this? It will explode. So the only c that for which it won't explode is when c equals 0. Good? Okay. Now what if I multiply it with c? Okay, now it depends on what the c is. So if c was equal to 1, then the number doesn't change at all, it just stays the same. When c was equal to 2, then it just explodes. But when c is equal to half, it keeps getting smaller and smaller and smaller and becomes 0. So something interesting happens. So now, here is the next simplest example, which is we will square the number and then add c. Okay? So for c equal to 0, what happens? For c equal to 1, what happens? For c equal to half, what happens, etc. This is what I might want to understand. Now, turns out, if you try to do this, it becomes a very complicated process. So I'm going to show you this as a demonstration. Okay, so I've just written this, I didn't write it, Claude helped me write this. So what I'm doing is wherever my mouse is what my c is going to be, and I'm just marking out all the values that you get for the next 50 iterations or something. Okay, so for example, if you look at what is going to happen for whenever c is here, they all seem to converge to some point, right? But the moment c goes somewhere like here, it suddenly starts shooting off. Okay, but if c is here, it seems to oscillate between 2 points. Okay, and when c is like somewhere here or something, it oscillates now between 4 points. Some bizarre thing is happening, even if you slightly change it, suddenly something completely crazy happens. So we could ask, what are the points at which it stays bounded? Where all does it explode? So if you do that, you get some figure like this. And this is what is called a Mandelbrot set. It's a completely crazy fractal. Okay, there's all sorts of so intricate details around the boundaries, etc., where this very, very simple dynamic function, which is just z squared plus c, behaves in bizarre ways with respect to this. Okay, so this is what a Mandelbrot set is. Okay, I've told you what a Mandelbrot set is, and you might be wondering. Okay, so there are some questions that you could ask, but of course your question at this point will be, dude, where are the card tricks? Okay, so I'm going to show you. I don't think I'll have time to show all 4. So I'm going to show you the most mind-blowing version of this card trick. I'll do that first, which is called Up the Ante by Martin Smith. And I'll also show Aunt Mary's Terrible Secret, but I'll show like a small version of it. And I will let you look up these two. There are plenty of YouTube videos about these card tricks. You should look it up afterwards. Okay, so let's show up the ante. So how many people here are card magicians? Whoa, okay, I'm scared now. Okay, there's one, okay, two. And how many people have sort of played around with card tricks at some point in this thing? Okay, good. So I'll end up needing some volunteers. I just want someone who can shuffle the deck well. Okay, good. So, okay. So can someone just name like a number between, I don't know, let's say 15 to 20, 15 to 25 sort of a thing? 17, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay. What's your favorite card? Huh? Queen of which? Queen of Spades. Would you be impressed if the next card was the Queen of Spades? Okay, sorry, I'll just move to... Okay. If the next card is the Queen of Spades, would you be impressed? Okay. That will be a great trick, but it's not. Okay. So can you just help me? Actually, let's add a few more cards here. Can you just riffle shuffle this? Don't close it already. Just do a riffle shuffle. No, just put it on the table and just. Okay, good. So I just want people to see that this is actually a legitimate riffle shuffle. There is nothing like, it's not like exactly one after another or something. Okay, so thank you for the moment. I might call on you again. Okay, so here is the thing. This trick is called up the ante. I'm going to make a series of predictions. Okay, imagine you can put some virtual money to play in this game. Okay, at any point, if you want to get out of this game, or rather if you want to say, now I'm definitely in the game or something, you should put your hand down. Okay? Like initially let's imagine all of our hands are up, and as and when you feel like, okay, now it is getting too much, etc., you can put your hand down. Okay? So what I'm going to do is I'm going to take the top two cards, and I claim.
So that's just a randomly shuffled deck, right?
Yeah, I had a deck in some, you could have thought that I have a deck in some order, but she came and shuffled it right now. Yeah, I'll tell you exactly how it works. I'll tell you exactly how it works at the end. Okay, so there are two cards here. I claim there is one red and one black in it. Okay, if I am right, and if you play in this game, let's say you have to give me 5 rupees. But if I am wrong, then you get 5 rupees. Okay? Okay, at this point, it's like, what is the point of getting into this game at all? Okay, maybe it's not good enough for you. Sorry. I'm going to put two more cards, and I claim this is also a red and a black. Whenever you feel like you want to get into the game, you can lift your hand. Okay? Let me make it even sweeter for you.
So what's the goal of it?
The goal is for you to get money from me. So there was a deck that was shuffled, and I am putting out a sequence of predictions. And if any of my predictions are wrong, you get money from me. If all my predictions are correct, you have to. So at the moment I am claiming there is a red black here, 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 red black here. So then even if one of them is not red black, I'll give you the money. If any of my predictions are wrong, I get to give you money. Okay. Okay, some of you are still not lifting your hands. So here is the next thing. So 1, 2, 3, and 4. I claim there is 1 clubs, 1 spades, 1 hearts, and 1 diamonds in that. Okay. This has 1 clubs, 1 spades, 1 hearts, 1 diamond. This has 1 clubs, 1 spades, 1 hearts, and 1 diamonds. Okay. You are still not lifting your hand. So there's 1 more. Okay. Right now, how many are there? So, sorry? Okay. Is there anyone who is still not lifting their hand? There are people. Okay. So here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I claim this is ace through king. I have exactly 13 cards left with me. Okay. I claim this is ace through king. Okay. there are still some people who are not lifting their hand. So let's just see how well we did in this thing. So just want to make sure people understand, we started off with the deck, she came and shuffled it, and after that all of these predictions are happening. Okay, that's a red, black, red, black, red, black, red, black, red, black, red, black, red, black. Okay, now there is supposed to be spades, hearts, clubs, diamonds. Space, hearts, clubs, diamonds. Space, clubs, okay. And this has, I have several more. Wait, I am coming. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King. Okay? So this is the trick called up the ante. Okay, how many people have seen this trick before? Yes. Okay. Okay. Okay, good. So this is the most fun part of the method I'm going to show you. This is the most interesting part of the trick. Now let me show you one more, the simpler version, because that's what I'm going to explain. Okay, when I do the explanation, I will tell you how that works. But by the end of the talk today, you will know how this trick works. You can go and show your friends. Okay, so this trick is called up the ante, I don't know, it's called Aunt Mary's Terrible Secret or some such thing like this. So once again, I need someone to come and riffle shuffle the deck. Okay. Okay, so I'll tell you what the trick is going to be. We are going to place 2 cards at a time. If it is red, red or black, black, you get a point. Okay? If it is red, black or black, red, I get a point. In fact, let's say if it's red, red or black, black, you get 1,000 points. If the colors are different, I get a point. Would you want to play this game? Well, you shouldn't immediately, because I have though carefully arranged it as red, black, red, black, red, black, red, black. And then you'll be like, "Arey, dude, what? This is not fair." So I want someone to come here and riffle shuffle this deck. No, I'm going to use this deck. So can someone come and riffle shuffle a deck? Who? Volunteer? Yeah. Huh? No, I'll show you. After the riffle shuffle, we will look at the deck and then we'll see what it's like. So just cut some part of it and just riffle shuffle those two together. Yeah. Okay. So yeah, it's fine. So let's merge these together. And now let's look at the decks. For example, there is a black, black here. There is a red, red here. Because it won't be a perfect shuffle, right?
So but you just shuffle one more time. Do it like a
No, I decide what the trick is. Okay. So for example, there is a black, black here and stuff. So the riffle shuffle, the point is, even if I started off with the new deck order, I mean in the sense that it's red, black, red, black, after a riffle shuffle, there could be blacks together, there could be reds together, etc. Right? So now let's play this game. Okay? Okay. 1 point for me, 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 1 point, 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 1 point. Oh, sorry, this was the other thing. Okay. So yeah, so I got 26 points. So this is called Aunt Mary's Terrible Secret. This is just one phase of that trick. Okay. Okay, we've seen 2 tricks. There are several more that use the same principle. Okay. So hopefully it went well. So many of you might be wondering, how the hell did you do that? Okay. So let's think through and let's think about what could have happened. So we'll focus on the last trick because that's the easiest to describe. Okay, let's reconstruct what happened. So we took a deck of cards and an audience member was asked to come and shuffle it. Okay, and somehow all adjacent cards turn out to be red and black. Okay, and you might be wondering, okay, maybe, of course I didn't want to use his card, I wanted to use mine only. So you might be like, okay, maybe I came with a properly stacked version. Like I set up the deck in a certain way, but you'll be like, no, but that guy came and shuffled it. Okay, so how can this still happen? In fact, I showed you that there were adjacent cards that were of the same color or so on. What went on? And then you notice that the last thing is not quite correct. It's not that I and I plus 1 always have the same color. It was like 2i minus 1 and 2i have the same color. That is, it's not like, it's possible that 4 and 5 have the same color. That is possible. All I'm saying is like 1 and 2 are different, 3 and 4 are different, 5 and 6 are different, etc. That is, the first one being an odd number, second one being an even number, that I'm saying is different.
You pick 1, 2, 3, 4, 5.
No, I'm just saying that 1, 2 is the first pair, 3, 4 is the second pair, 5, 6 is the third pair, etc. Every such pair was different. Okay? So basically what we are going to understand is, okay, if we start off with some nice stack and we do a riffle shuffle, what are properties that are maintained, okay, in the process? What is the time? Okay. Oh wow, I'm almost running out of time. Okay, so this is this person called Norman Lawrence Gilbreth. He's a really cool mathematician and also a magician. In fact, he is often referred to as he happens to be a mathematician, but he is a lifelong magician. And he published this principle in an official publication of the IBM. IBM is not the computer company. It is something called the International Brotherhood of Magicians. It's actually a real thing. And he published this particular principle in a magazine that's called the Linking Rings. And since then, this has been a core of so many card tricks. Okay? He's also known for his mathematical work. There's something called the Gilbreth principle involving prime numbers or something, but who are we kidding? So let me tell you what the Gilbreth principle is. Okay? So we will take a deck to start with in alternating red-black order. Okay? We will now cut the deck into two parts, just ensuring that the bottom two cards are of two different colors. You may not have seen me do this, but we will just cut it such that, at the bottom there are two different colors. And now we riffle shuffle them together. Turns out, 2i and 2i minus 1 and 2i will always have two different colors. This is what the baby version of the Gilbreth principle says. And we are going to see a proof of it. So let's imagine this is what the two stacks look like. There's a bunch of black, red, black, red, black, red. This one look like red, black, red, black, red, black. All I'm insisting is that the bottom two colors, they are different. All right? Now when we riffle shuffle, what can happen? Let's look at the bottommost two cards. What could those two cards be? Either those two bottom cards came as the bottommost two cards, in which case, of course, it will have two different colors. Or maybe the bottommost two cards came from the same stack. Now also it has two different colors. Or it could be from the next stack. Now also it has two different colors. So you just keep doing this again and again and again. It's possible that some of them look like black and red, some of them look like red and black. That's possible. But if you look at a pair of cards, like from the bottom, it will always have one black and one red. Yeah, okay. So that's it. So basically this is this is how the trick, the Aunt Mary's terrible secret trick worked. I set up initially in red, black, red, black, red, black. I could call anybody to riffle shuffle. The only thing I have to make sure is that when they riffle shuffle it, they are riffling shuffle it with the bottom colors being different. For example, if the bottom were both black, black, the bottom two cards could have been black, black to begin with. All good? We'll come there because there's going to be 13 colors eventually. I mean, ace through king, they're all colors anyway. So we're going to get to that. Okay, so here is a toddler version, which is actually what I did here. Now suppose, once again, we start off with a deck in red-black order. Now we didn't bother about checking if the bottom two cards were of the same color or different colors. We just let the person shuffle. That's what happened now. Okay? But after the person shuffled, I'm going to carefully look at the deck, find one place where two colors were the same, and I'll cut the deck at that point. So when I was showing you the deck, I said, look, here there are two red cards. But then I put it back the other way. That's the one cheating thing I did. Okay? Once again, 2i minus 1 and 2i will have two different colors. Okay? I leave this as an exercise for you to figure out why. Okay? So this is what is called the Gilbreth principle. You might be wondering, okay, all this red, black and all is okay. Tell me how the up the ante thing works, because that was probably way more impressive, right? So the general Gilbert principle is a little more complicated. I'll just show you them by examples. So the general principle says the following. Okay, what is a Gilbert shuffle? A Gilbert shuffle is going to be the following. You take a deck of cards, split it into two parts, but before you riffle shuffle it, you reverse the order of the first part. So I was doing this stupid nonsense of asking people to give me a number and saying what's your favorite card, etc. Right? That was just an excuse for me to reverse the cards. Okay, so that was the cheating thing that I did. That's what I did there. But you start off with a deck of cards, you cut it somewhere, you reverse the other part, and now you riffle shuffle them. That's what is called a Gilbert shuffle. Okay, that's what we had done in the up the ante. Maybe you didn't realize that, when I was asking for numbers, that's really what I was doing. Okay, so Gilbert shuffle says the following. If your cards were originally set up such that blocks of B cards are repeating in some specific order, turns out after a Gilbert shuffle also, every block of B cards will be exactly what you started off with. This looks like a lot of words. Let me show you in examples. So if your cards start off with red, black, red, black, red, black, red, black, you do a Gilbert shuffle. At the end of it, every pair of cards starting from the bottom will have one red and one black in it. It may be in two different orders. That's okay. So if your cards start off with clubs, hearts, spades, diamonds, clubs, hearts, spades, diamonds, clubs, hearts, spades, diamonds, and you did a Gilbert shuffle, every block of 4 cards from the bottom will have one club, one hearts, one spades and one diamond. It could be in a different order. That's okay. And if your cards look like ace through king, ace through king, ace through king, ace through king, and you did a Gilbert shuffle, at the end of it, blocks of 13 cards from the bottom will have exactly one copy of ace through king in it. Okay? So this is the full-blown version of the Gilbert principle. It's a surprisingly not so well-known mathematical principle, but with this thing you can build so many card tricks. Okay? So why does this work? And in fact, it's exactly the same argument as last time. So let's just do this for clubs, hearts, spades, diamonds. We'll just try to show that, we'll start off with some deck that looks like this. We will do a Gilbert shuffle and we'll convince ourselves that every block of 4 cards starting from the bottom has one club, one hearts, one spades and one diamonds. Okay? So we'll cut here. This is just the first half. I've written it below. And the other one I've just reversed and put it here. Now let's imagine doing a riffle shuffle, like this. Okay? Now let's ask ourselves, what is the bottom 4 cards going to be? There are several possibilities. Maybe the bottom 4 cards looks like these 2 and these 2. That's what comes up in the bottom. Okay, fine. But that, technically speaking here, it looks like this bubble. It's a bubble of 4 cards. Because I started off with clubs, hearts, spades, diamonds, clubs, hearts, spades, diamond. This bubble will definitely have one club, one hearts, one spades and one diamonds. Okay? Or maybe the bubble looks like this. Maybe the bottom 4 cards look like one fell from here, 3 of them fell from this other one. That's just a slightly different bubble. But that bubble also has one clubs, one hearts, one spades, one diamonds. So you remove this bubble, continue. That's it. That's the full proof. Basically, if you look at the bottom 4K cards, essentially it's going to be one bubble of length 4K that's present in the original pack. And because it was periodic, of course it will have exactly one copy of each of them. Or rather K copies of each of them. That's it. And so therefore, now if you want to do the up the ante trick, okay, what should the deck have initially been? Good. So one thing it should definitely be, because there was also a red, black, so it certainly has to be red and black alternating. Additionally, it should also be clubs, hearts, spades, diamonds, clubs, hearts, spades, diamonds, etc. And ace through king. So you need to find an ordering of 52 cards that looks like clubs, hearts, spades, diamonds, clubs, hearts, spades, diamonds throughout, and also looks like ace through king, ace through king, ace through king, ace through king throughout. And because it's clubs, hearts, spades, diamonds, it will automatically be red, black, right? So for up the ante, just set up the deck this way. Just have ace through king, ace through king, ace through king, ace through king, and now put one after another. In fact, what I had done, the reason why I had so many decks and reason why I didn't want to use your deck is because, each of these decks are arranged in a very similar order. Okay, sorry. Let me. Yeah. So each of these decks follow a slightly different order. So this is what I have. So this is an order which is called a Sayce-Stebbins order, named after a person, Sayce-Stebbins. But can you see a pattern in? It's a gap of 3, basically. It's the same thing. So basically think of it as clubs, hearts, spades, diamonds throughout. But the instead of ace through king, I'm just looking at it as ace 4, 7, 10, king, 3, 6, 9, queen, 2, 5, 8, jack. And that's what is happening here. So this is called the Sayce-Stebbins stack, and as you notice that it's like a plus 3. The reason is that it's very easy to get to Sayce-Stebbins stack if you have a deck in full deck order. You can think about exactly how to do that. That's the reason why, in fact, there are like whole magic shows that are arranged with people bring a deck in new deck order. They will do 2 or 3 tricks where they are doing some very careful shuffling, and after 2, 3 tricks, somehow the deck comes to this order, and then they will do up the ante. And the mind will be blown for people because we've just been shuffling the deck for the last 3 tricks, but it's all very carefully arranged. So, so people who are interested, they can look at this. So this is an example of something that has all the options that you wanted for up the ante. It works. So the only thing to make sure is the order in which you put down the cards. So the way I did it was I put 6 pairs of 3 cards each. So that was a multiple of 4. So then I could put 3 sets of 4 cards each. So that's still a multiple of 4. Now we got 24 cards. But I need to get to the last 13. So I need to get rid of 26 cards now. So I put 1 more pair and then 13. You can figure it out. Think about it more, you can figure it out. Okay? So what I worked with is something called the Sayce-Stebbins stack. Okay? None of this is important. Okay? What has this got to do with the Mandelbrot set? How much time do we have? Okay, let's maybe see this a little bit. Actually, no. I'm not. There is a way of connecting the Mandelbrot set with these Gilbreth permutations. I don't want to go too much into it because I don't know if people have questions or they want to try out something or whatever. So I'll leave that open. So I'll go back to hobbies a little bit. So a little bit about me. So I don't have a good definition of what a serious hobby is, but I have an inkling of what they should be. Okay, and to be honest, I have a lot of hobbies, and in fact my wife keeps mentioning that I go through these hobbies roughly once a year. Like there'll be 1 year when I'm just obsessing about something, and then I'll keep, like for example, there was a time when I was just obsessed with knots. So there were so many shoelaces at home. I will be trying various kinds of knots. There are these hitches, then there are these constrictor knots, and there are like these bowlines and all sorts of things. I was just playing so much with knots. Of course, I still continue to play with cards because this is something that I picked up during the pandemic. I had nothing better to do, just watching YouTube videos, and that's how cards, etc. happen. I have a lot of Rubik's Cubes at home of various things. I keep playing with them. That was a phase at some point. Right now, do people know what this is? Okay. So this is something called a Raspberry Pi. So I have a Raspberry Pi at home, and every 3 days or something I have to apologize to people at home because the internet has stopped working, because I was doing something here, something broke, and I have to tell them, please give me half an hour, I will fix it, and so on. So this is what I have been playing a lot with. And of course there was a point when I was obsessed with chess when I was in school and stuff. So here are some commonalities between all of these hobbies, at least the way I approach these hobbies to me, and maybe some of this resonates with you. So the first thing is, if you ask me why I am doing it, I don't really have a good answer. It's just that I like it. Okay, the motivation is extremely intrinsic. It's not something that you can often justify to somebody else as to why is it that this is something that you are so, interested in. The other thing is, almost all of these things I'm actually not good at this. Okay, but the point is, it doesn't stop me from doing it anyway. Okay, like in the sense, every other thing, it somehow feels like you get more interested if you're good at something because the validation somehow helps. But hobbies turn out to be something that you're doing it just for the fun of it. And the fact that you are not good at it or something is just it's not something that you're factoring into account at all. Okay. And some of them, people might say that, oh, no, if you are very good at chess, you will become a good strategic person or something. But honestly, I don't care. I mean, there may be practical applications of all of these things, but I'm doing it only because I like doing it. That's it. Okay? And most of the time, mastery is not the goal. I'm not playing chess because I want to become a grandmaster. I'm not doing card tricks because I want to do shows elsewhere. But what I want to see myself is I want to see myself improve. Like there was some state at which I was the previous day, and I just want to see, am I learning something new today? So that becomes often the goal. And to be honest, it might be great to sort of do these sort of talks and where I can give these card tricks. But if you come into my home at some point and see what I'm doing, most of the time I'm doing some stupid practice move. Okay, it's just a completely mundane sequence of moves that I'm just practicing. Even when it comes to the Rubik's Cube, I'm just practicing the muscle memory of one sequence or something. It's like a very, very unglamorous thing that you're doing throughout your life. Occasionally there will be a show where you show some card tricks, but that's about it. Okay, so the process of improvement is really not glamorous. Okay, and the reason I'm saying all this in this context is because I often think research is a very, very similar thing. In the sense that it's very hard for me to describe to people why the specific problem that I am researching on is important. And I am willing to tell you why I am excited, but often I am not interested in convincing you that this has to be a good thing. Okay? It's just that I like doing it, and many of these research problems I wasn't good at some point. It's just that I kept improving every single time. Okay? So in my opinion, the reason I ask people about hobbies is because it often tells me a sense of their attitude towards research as well. Because I just think that we often nowadays in these movies and so on, we romanticize research a little too much. And I just want to sort of say that it's a beautiful thing once you have the right expectation. Okay? So let me give you an example. Okay? Most of it is like, this is like very high-end mathematics, but I'm going to give you an example to start off with. So if here is some three crazy numbers, e power pi square root 43, e power pi square root 67, some random number. And if you use the calculator to figure this out, the first number turns out to be something 0.9999 something. The second number turns out to be something 0.99999 something. The third number also looks like, this thing. So when you see numbers like this, you will immediately be wondering, why the hell are these almost integers? I took an e, I took a pi, I took some square root or some nonsense. Why the hell will this thing actually be an integer? Okay, it's not, if it's an integer, it would have been one thing. Why is it almost an integer? Okay, so maybe people had this question, then you might go about asking, okay, I want to understand this, how do you go about solving this? And people will often tell you, oh, there's a 744 that's coming in all of them. People will tell you, oh, in order to understand this properly, you need to understand something called group theory. And you'll be like, oh, okay, group theory, maybe, it doesn't seem that complicated. They say, oh, you also need to understand complex numbers and complex analysis. You'll be like, okay, that is also fine. And then they will tell you, you need to understand something called modular functions. And you'll be like, what the hell are modular functions? Okay, a modular function is a function that is periodic and has some reflection related symmetry. The first one, it's a function such that if you increase the value by 1, the value doesn't change. The second one is if you start off with a complex number here and you look at a mirror image of that complex number, they both must be related or something. There's some relation with regard to that. Okay, you might ask, what is this? Can you give me an example? Whenever someone tells you this is what your function looks like, you might want to know what is an example, right? Like if it was just this, I would have said, take something like sine pi x or cos pi x or something. But with this also, like what is the simplest function? Turns out the simplest function, are people taking notes? The simplest function is this. Some completely crazy thing. This is the simplest modular function, okay? And if you work out this modular function, you see some 744 and some things. Okay, non-constant. I should have said non-constant modular functions. Yeah, okay. So this is what it turns out, and apparently this is the reason why all of them are almost numbers, almost integers. Doesn't matter, okay? And these, for people who are familiar with group theory, these numbers are somehow, they are related to something called the monster group. That's literally what that group is called. It's called the monster group. So people were wondering, do these modular functions have anything to do with the monster group? And when someone made this conjecture, it was called the moonshine conjecture, because moonshine is like, this miracle that you're expecting to happen. There's just no chance that this will happen. It's some crazy coincidence. But turns out that conjecture was true. And Richard Borchard's, by the way, he has an incredible YouTube channel. I will highly recommend people to watch it. He actually got the Fields Medal for a variety of things, one of which was proving this moonshine conjecture. Now, the reason I'm telling you all this is the following. If you look at Borchard's proof, most of the proof will involve this nonsense. Now, is it glamorous? I mean, to looking at this and sort of making some small algebraic manipulations and trying to understand this or something. But does it change the fact that these crazy things are being almost integers? Isn't that beautiful? So the point I'm trying to make is that it's often the case that the end goal might be really beautiful, really wonderful, and so on. But often the path that you take to it is a very unromantic path. Okay, and it's very hard for, I mean, if you come in with the view that, you want to just solve beautiful stuff, I mean, most of the time it won't happen. So what you should pay more attention to is, do you like the process of learning stuff? If you like the process of learning stuff, no matter where the journey will take you, you will love it. Okay? So some commonalities that I will sort of list out is that both for research and for serious hobbies, it requires a lot of effort. It requires a lot of what I will call deliberate practice. Okay? Like, I don't know if people have gone for music classes or something. We spent years and years initially learning Sarali Varasa and like whatnot. I mean, like, it's just boring. But the thing is, that's the deliberate practice you need when you move to possibly more complicated songs, etc. And the learning curve is never ending. But by that, what I mean, it's not like you are constantly improving. There will be plateaus. There will be a point when initially you were like, oh, I learned 2 tricks and suddenly I'm here. And then for the next 2 months, nothing. I mean, you are at exactly the same state. But you need to just keep persisting. Sooner or later, you will get out of that plateau. And then you will go to the next this thing and so on. And there's a lots of trial and error. And something that is really understated is the fact that there is a lot of unlearning. Like, if people have played badminton, there was a point in school when I used to play badminton, I was reasonably okay at it. And then at some point, someone told me I was holding my racket wrong. Now, the point is my entire muscle has been adjusted to this wrong holding of the racket. But the only way I can now start improving is if I start holding a racket where the racket looks like this. I know people who play badminton might realize that there's a certain way in which you hold it so that your backhand shots are, more powerful and stuff. So there is this, I remember this thing where when I decided to start holding the racket properly, the next 3 months were horrible. I am losing every game. Okay, but that's how it works. I mean, like, if you want to improve, you sometimes have to step back, unlearn, and then proceed. Okay? And it's extremely frustrating, it's extremely tedious. Now, why am I saying all this rather than motivating you all to do research? I don't mean these as bad things. There is a lot of joy that you have over the process, but not the product. Okay? It's this journey that you should be enjoying. Okay? Occasionally, we might prove beautiful stuff. That's incidental. But what I do every day is just trying to see, okay, yesterday I didn't have clarity on something. Today, do I understand that better? That's what the journey sort of looks like. And it's not really about this talent, this person is gifted in this particular field or anything. What really matters at the end of the day is persistence. All of these other aspects, it's like, you're running a marathon and someone has a 100-meter head start. All of that doesn't matter. It's a question of, are people willing to put in the work every day subsequently? So it's the persistence that is the most important thing when it comes to research, especially when it feels like nothing is happening. Okay? And something that I absolutely enjoy is that I find the community of researchers to be extremely welcoming. It feels daunting to maybe write to a random big person and sort of say, I have a question in this. You would think, why would they want to answer you? You will be more surprised about how many times, very, very, simple acts of kindness have led to completely drastic things. And this I'm saying from my personal experience about, there's so many things about where I have eventually landed up that I will attribute to some small conversation I might have had in school with somebody or some uncle of mine, etc. Okay? So what I want you to take away is that research is an extremely rewarding experience. but only if you have the right expectations. I mean, okay, and just last year, I came across this blog of Chavi Yadav. So Chavi Yadav was a person who just completed her PhD in something involving AI, particular optimization problems in AI. And after her PhD, she wrote a blog post. And it was called The Margins of My Dissertation, Life Lessons That My PhD Taught Me. And in my opinion, everything that I wanted to tell students who wanted to come and work with me, she has articulated it better than I could ever have. So I just want to read out what she says. Okay, do I recommend doing a PhD? Only if you know it's going to break you and rebuild you in ways you didn't expect. If you come in with a romantic and rosy idea of research, it will shatter immediately. But if you're if you're curious, willing to unlearn and open to being reshaped by failure and growth, it can be profound. So just don't go in expecting only answers. You'll come in with better questions. Okay? So let me just stop here. So this talk was not about chaos theory or complex dynamics or anything. It's not about the Mandelbot set. Yeah. So I will meet again. I'll tell you a different sort of card trick at that point. By the way, the connection between Gilbreth and this thing is by a theorem by Milner and Thurston. There's so many stories I can tell you about Bill Thurston. Bill Thurston is again another Fields medalist. But probably one of his biggest, in my opinion, a contribution that made such an impact on me is do people know this thing called Stack Exchange, where people ask questions? So someone asked a question saying, I am an undergrad who wants to do PhD in mathematics. I see giants who are working on hard problems. What is it that I can contribute? When there are these big people who are working on this. And you should just read the answer that Bill Thurston wrote. I mean, it tells you what the passion about teaching really is like. I mean, I'll just let you look at it. So anyway, so what I wanted to show you was some mathematical card tricks and possibly a connection to serious hobbies, whatever it is, and maybe what to expect and what especially not to expect from a career in research. Okay? So in the next hour after the lunch break that we meet, I will tell you one more card trick. This may not involve so much of, it involves a magician and an assistant, and my assistant is going to be Claude. But we will see some things, and I'll also once again try and connect it with some topics that you've actually seen in the last month by various courses and stuff. Okay, so that's all I wanted to say for now, and thank you. Questions? Any questions for now? Okay, so I'll maybe the decks that I have messed up, I will keep them aside, but there are a few more decks in the Stebbins stack. If any of you want to play around with it, I'll just leave it here. I mean, anyway, we can meet post lunch for the next session. Okay, thank you.